All right. Hello, everyone. Thank you for coming to our session. My name is Ezekiel Lanza. I am an open. You can hear it? You need to wear this. Yeah. Because you can all hear me, right? Yes. Great. Thank you. So again, my name is Ezekiel Lanza. I am an open source AI evangelist, and today with me will be joined John Handler from Amazon, is a director of technology of OpenSearch, Anthony Vance, which is a principal engineer of Intel, and we'll be talking about how to simplify the deployment of Gen AI applications using OPEA. But before diving on that, this is the agenda, right? So we start talking with the challenges. If you are developing something with Gen AI, you can face the challenges. So we'll be talking a bit of the challenges. We'll be introducing the project, the open source project that is OPEA. Now it's just a name or something, but you will learn way more during the talk. How OPEA integrates with AWS. John will be talking about OpenSearch, or the contribution that they made to OPEA. We'll do a demo at the end. If we have some time, we'll do a quick demo, very quick demo, at least 5 minutes, 10 minutes, we'll see. Call to action and the closing. So if you're working with Gen AI, you may see that there are some problems when enterprises would like to get the value of those applications. We can know that we would like to use RAG application, chatbots, video Q&As. I mean, Gen AI, we see that it's very attractive, but we don't find a way. Enterprises are struggling to exactly get the value of Gen AI. And this is all the times, it depends on the technology or depends on the framework or something, but most enterprises, they are facing that real problem is the technology. And actually the technology itself, and Gen AI is not just one thing. We can see every time that we are deploying, we will go in the details, is that we have multiple moving pieces when we are building those applications. It's not just one component. We have 10, 20, 25 components, and if those components, they cannot integrate each other, if they cannot talk each other, or if they are not compatible, we'll have a problem when we are deploying that as enterprises. So these are very nice slides, but the Lego analogy is like you like to have pieces that they can easily integrate between one and another. But why we are here today with AI is in just 2 years, or we can see 5 years, we can see an explosion, right, on everything that is around AI. We can mention on the one OpenAI launched ChatGPT, or the transformers. I mean, I will not go into the details of this slide, but it's basically we are overwhelmed. We have tons of technologies, options, frameworks, models that we don't know how to choose which is the best one or which is the most suitable for our use case. So when we are today is that from 2 years, and probably most of you remember, ChatGPT was launched 2 years ago, right? A bit more. And from 2 years from now, we've seen that explosion. We've witnessed that explosion. And if you are working with an enterprise, you will see that you have multiple options. And if you would like to start something, you will need to build the application from what you think that is the best path or the best way to organize it. So you'll be constantly like kind of reinventing the wheel because you don't know what to do or how to do, so you try to do some research and you see, okay, this is the best way to do it. There's no too much best practices. This is another challenge that we used to see. So we are saying that this is a problem that we are all facing, but there's a huge opportunity to try to work together as a community, as an environment, to try to build something that can be benefited for all of us or for all the ecosystem. And we have these Legos, these de-organized Legos, and sometimes when you are with enterprises, we ended up with something like that, with something that it's not great, but it works, right? So we start to pick the pieces, all the de-organized pieces. It works, but what happens if you are an enterprise and you would like to add a new feature? You would like to add or to modify one part. That could be a complicated thing. So the main thing, or the most important thing from companies is you need to have a solid base. You need to build something on top of standards, because if you need to modify it, can be very easy and very simple to modify something that you may have. But there's a platform that can help you on that, a framework, an open source framework. The important highlight here is we should come with a solution as a community, not just one company proposing something, not just one person, something that is a collaborative effort that we all should participate. All the companies should participate to have like a framework or something. And this is what OPEA actually is. OPEA is an open source framework that is part of the Linux Foundation, which the main important thing here is that it helps you on the deployment of GenAI applications, but in the end-to-end of GenAI applications. It's based on microservices architecture. So each building block of your application, I suppose you have a RAG, we'll talk later about the architectures, but each building block can be replaced and can be used. For instance, if you like to use an LLM or a vector database, you have a particular component that is optimized for something special. And you can plug and play the component that you want to build your own application for your own use case. There is some examples. We'll go into details later, but this is a collaborative effort. So it's not just Intel, it's OpenSearch, it's AWS, it's Neo4j, tons of partners that are part of this project that we are all building together this set of blueprints or best practices. So any person, any company, any enterprise can pick those examples and can deploy it. Before diving in this part, in the RAG part, I want to make a question. Please raise your hands. How many of you know what RAG is? Oh, that's great. So you are very familiar with this. Nice, great. So this is a blueprint of a RAG application, right? So you have the microservices you have a retriever, you have a re-ranking, you have embeddings, you have an LLM. Then how OPEA treats each particular part, or a particular block that you see is one block that a partner contributed to the entire solution, right? For instance, if you would like to use a vector DB, you can use Redis, or you can use OpenSearch, or you can use MongoDB, or whatever. And if you would like to replace it because your use case prefers to use any other vector database, you can easily replace and the example will keep working, right? So I don't have to explain that, but think that you have a flexible architecture. And the main goal of this, and this is why it's an open source project, you would like to avoid two things. One is the vendor locking, because you don't want to have your solution locked to a platform or locked to a vendor. So I like to have the freedom to pick whatever option you can use for your application. And the other benefit is that it will help you on the time to market. If you're an enterprise, you would like to find something really fast to deploy. You don't want to reinvent the wheel. You want to have something that helps you to accelerate or to speed up your GenAI deployment. And this is just RAG. OPEA has more than 20 different GenAI examples, like video Q&A, visual Q&A, agents. But this is the more that helps you to visualize what actually OPEA is. And this is one example, right? So if you go to the repo, that we will send the links later, you can see that there is a blueprint. OPEA provides blueprints, end-to-end blueprints. And for the chat Q&A, which is the simple RAG application, you have a blueprint, right? And this blueprint, for instance, is using Redis as a vector database, as a retriever, as a re-ranking, and is using Hugging Face, which runs locally in the cluster that you're using, but it's using Hugging Face. So you can use any model that is compatible with Hugging Face to use your inference. Sometimes you would like to use Llama, sometimes you would like to use a 7 billion parameters. So you can easily say, I would like to use in my architecture this model. It's just an environment variable, and you can use that. Same for embeddings, but you have options. Right? So if you like to change the vector database, you can use any of those vector database to replace your Redis example, for instance. And these are why you have those options is because you have partners that are part of the project. So these are all the partners that contributed something to the project, that contributed a part, or that contributed their component or their optimized component for any kind of solution that you can see in the OPEA blueprints. So what I want to highlight here is you can see the different names, and this is mainly the goal of OPEA is to give you options when you would like to deploy a GenAI application, right? So I'll pass to Anthony, which will be talking about AWS and Intel.
Hey, good afternoon, everyone. Thank you, Izzy, for giving a nice introduction to OPEA and taking us through what involves in developing with OPEA.
That's right.
I'll be talking more about the Intel contribution to OPEA and how Intel and AWS are partnering to develop the OPEA platform. But before that, I would like to add a few points and taking you through the typical developer journey and how OPEA helps. Then we can go into Intel and AWS contribution to the OPEA. This is from a developer perspective, right? Typically, when you're building a generative AI applications, when I say application, it's not just creating a prototype, but also going to the production, right? Because you could build a simple application LangChain, right, to the RAG pipeline. But if you want to take the RAG pipeline to a production, there are many things you need to consider, right? You need to figure out, well, how you're going to create an authentication authorization pipeline and how you're going to take the microservices, scale it with Kubernetes, right, and orchestrate so that you can have a production level application, right? So to develop this application, a typical developer spends months of development, right? You start with open source component and you try to integrate, CSP managed services, but getting to the production level quality always takes time, right? That's why when you are using OPEA, the OPEA is not only targeted for the developers, but it is also targeted for the enterprises, right? So OPEA end-to-end application, if you're taking an end-to-end application in OPEA, which comes up with well-validated microservices, because there is a CI/CD pipeline running into the OPEA platform, and also you have a well-validated end-to-end examples, right? And there are partners contributing to the OPEA GitHub and the repository. That creates a really larger community. So these components kind of reduces your development time and creating a developer efficiency. With that, I'd like to spend some time just talk about the Intel and AWS partnership. Intel and AWS have been partnering for about 18 years plus. And the partnership goes beyond silicon. You usually see that whenever Intel launches the platform, it shows up as an AWS instance, and you can start using it, but it goes beyond the silicon. You'll see in the bottom where Intel has enabled, Intel has been working with AWS Elastic Compute team and enabled instances for our 4th generation platform. It starts with general purpose to high memory instances, and we also have an AI accelerator, Intel Gaudi, which is showing up in Intel Elastic Compute. So in addition to enabling the platform, we also work with AWS team to expose our accelerators. If you are using our Intel Xeon instances in AWS, you will see our AI accelerators like Intel AMX, and as well as we expose performance monitor counters, so that when a developer trying to optimize, they can look at the counters and maximize the application performance. On top of it, Intel and AWS partner to work on common runtime libraries. These comes by default in your AMIs and as well as containers. So when you're developing an application in these instances, these optimizations are baked in, right? And you get the maximal performance. Now, all these optimizations are by default propagated to AWS managed services. Let's say if you're using SageMaker, if you're using OpenSearch. These optimizations show up. So when you're using, let's say, an OpenSearch and deploying Intel instances, by default, they're optimized, because of the partnership, we have been having with AWS team. All right, so back to OPEA. So Intel has been contributing significantly in OPEA as an open source platform. And Intel has been contributing for a very specified curated stack. OPEA provides a choice of different microservices, and Intel has been contributing for a specific to Intel platform. And would like to start from the bottom. So Intel has been contributing to the microservices in OPEA platform for Intel Xeon and our Gaudi AI accelerator platform. And they are enabled by Gaudi software suite and as well as our own API libraries, right? So if you're picking up a microservices, they're optimized for that. So like I mentioned before, and if you see the stack, right, the stack comprises of not just AI services. For example, when you're serving an embedding, right, you need a good, the right software stack, which is enabled by text embedding inferencing from Hugging Face. Then the LLM inference is enabled by VLLM and TGA. These are open source component which Intel has already pushed in our changes. So when you are picking this container and microservices in OPEA, they are by default optimized. So in addition to deploying your AI services, which is embedding an LLM, it is important to have your optimized vector DB, which is enabled by Redis. And also these are enabled on Kubernetes so that you can scale it with Kubernetes platform. Also, let's say once you are going to the production, you do need to create a different user level in experience. For example, when you are deploying an application, you want to make sure that, hey, you give administrative access for few folks, right, and user access to a typical generic user, right? Or you need to create a different user profiles. So you do need a services for that. That's enabled by open source component like API 6 and Keycloak. Then, as an infrastructure engineer, you need to make sure that how the application is been utilizing the platform, right? And you need to look at the application monitoring and the performance KPIs, and they are enabled by Grafana and OpenTelemetry collectors. So these are contributed by Intel, and it is already baked into the OpenSearch, an OPEA platform. So when you're going to the OPEA, you will see different microservices for AI, and you will see a microservices for telemetry. You will see a microservices for authentication and authorization. Now, when you're bringing the stack to AWS, right? Now it brings AWS services and as well as platform. For example, the same LLM service can be augmented by Bedrock APIs, and that's applicable for embedding and as well as in LLM. Or you could deploy those embedding services into SageMaker instances. Similarly, the vector DB, you could use OpenSearch vector DB or OpenSearch managed services, and these are packaged and published in the marketplace using an AWS Cloud Formation templates. And for your authorization and authentication purpose, instead of using open source component, if you have already integrated in AWS IAM, you could just integrate them, right? So that stack kind of manifests into AWS managed services, integrated stack. Also, you can see in the bottom about all the Intel instances enabled in Elastic Compute Cloud, and these microservices can be deployed into the Intel instances as well. In a similar way, I would like to take you through a little more detailed blueprint of one of the OPEA example. Right. It's a little complicated, so I'll go section by section. If you see from the bottom, right, there's a web app. That's a sample UI, and you will see a similar application in one of our workshop that's going to happen tomorrow, 8:30 a.m. You'll see a QR code for that. So if you're interested, you could always go to the workshop and really look at these microservices deployed in AWS platform, and you could play with it. Now let me start from the top. So you have web app, which you can access anywhere. Then you have an ingress controller. Then at the top portion is like I said about the authentication and authorization, right? And you could create different user profiles, and they're enabled by open source microservices. Then the left side, you see the embedding and re-ranker microservices, which is integrated with the vector DB. And in this case, we're using Redis. And in the middle portion, you see the LLM services, which are enabled by the open source component like VLLM, and as well as OPEA has a guardrail microservices, which can be programmable. Then on the right, you have a telemetry services, right? They're all combined and create a nice blueprint, which you can access in OPEA right now. Now, when you're moving these blueprint to AWS, right, you do need to move each sections. You need to figure out, how these sections can be integrated into AWS, managed services, and as well as AWS instances, right? Which applies for security, embedding, LLM, vector DB, and as well as storage aspects. Now, the same blueprint kind of transforms into AWS instances and as well as managed services. For example, the security and authorization can be integrated with the API gateway and as well as AWS IAM, and your re-ranking and as well as the embedding services can be deployed into M7 instances. And for LLM, the OPEA application can get integrated into Bedrock APIs for LLM and as well as guardrails. Similarly, the VectorDB, the Redis can be replaced by OpenSearch, VectorDB, OpenSearch services, and for storage, you could use S3. So with that, I would like to cover how OPEA can be transformed into not just deploying into AWS, but is also a multi-cloud. Right? We are showing an example here where just an LLM inference is being deployed into a Denver DataWorks cloud. Now, then the LLM endpoints are exposed to the AWS application, which is running that OPEA example. Right? Now you have OPEA examples, OPEA application running in AWS, but just the LLM endpoints is being accessing another endpoint, which is hosted in the Denver DataWorks. Right? And if you look at Denver DataWorks, which is enabled by Intel Gaudi 2 AI accelerator, which is deployed with OPEA microservices, which are already published, which is available in Docker Hub. You take the microservices for LLM. In this case, it's using open source models like 70 billion or 8 billion, and also it's also enabled embedding services, which is enabled by TEI software stack. Now all these microservices have been fed into the authorization and as well as ingress controller. Now that exposes an endpoint. The endpoint is also secure endpoint with OAuth protocol. So when you're deploying application in AWS and as well as Denver DataWorks, right, they are secure. Right? Currently, these API endpoints which are exposed by Denver DataWorks are on private preview perspective. But if you want to know more about how to use this in inference API, feel free to reach out to me, or you can reach out to the email mentioned here from the Denver DataWorks. Also, these inference APIs are easily pluggable. They're OpenAI standard API compatible. Now, if you are deploying your application with OpenAI, you could just replace that with Denver inference API enabled by Intel Gaudi 2 accelerators, right? And your application will just work straight away. Now, I would like to go back to the same picture we are seeing, the full blueprint, right? Here, instead of Bedrock, it's calling the LLM API, which is hosted in Denver DataWorks with Intel Gaudi 2 accelerators. But now, the beauty of it is that the OPEA provides this flexibility, right? The individual microservices which are available now, and you could deploy either in an on-prem or AWS, and as well as a multiple cloud, right? So with that, I would like to pass on to John. John will take us through OpenSearch and as well as the deep integration of AWS and a contribution to the OPEA. Thank you, John.
Thanks, Anthony. Hi, everybody. Super weird to be talking normally to this room. Anyway, happy to be here today. Thank you for being with me. Today I'm going to talk a little bit about OpenSearch, give you a little bit of clue what OpenSearch is about, and then talk about how we integrated with OPEA and brought OpenSearch into the picture. So at AWS, we participate broadly in open source projects, both from a contribution standpoint and from a sponsorship standpoint. I haven't changed my slide. There we go. In July of 21, we introduced the OpenSearch project that was a fork of Elasticsearch 7.10, and we brought that out and got it to a stable running state. Last September, we announced the OpenSearch Software Foundation. This is part of the Linux Foundation, bringing open governance to the OpenSearch project. Project has been doing quite nicely. We have millions of page views, 700 million downloads, a lot of members, a lot of participating organizations, and with the foundation, we have sponsorship from 3 premier partners and a number of additional partners. So what is OpenSearch? OpenSearch provides 3 core capabilities. The first of those is OpenSearch is a search engine. And it provides you with structured and unstructured queries that give you lexical matching with adjustable ranking, the ability to run Boolean queries, support faceted, interfaceted search. You bring your data in, and we provide the search experience, much like you're familiar with across all of the searching that you do. Additionally, OpenSearch provides capabilities around analytics. You can run log data into OpenSearch and build visualizations, dashboards. It provides real-time alerting and the ability to monitor your software, your hardware, your applications, as well as distributed tracing to bring DevOps to what you're building. Finally, OpenSearch provides vectors and generative AI capabilities that enable you to build on top of it, both as a vector database and also providing a rich search experience based on nearest neighbor search with vector embeddings. So looking at the vector capabilities of OpenSearch, OpenSearch provides both exact nearest neighbor and approximate nearest neighbor with both the hidden navigable small worlds, HNSW, and inverted file, IVF, engines across, or algorithms across a number of different engines, including the FACE library and the Lucene library, and that enables you to do semantic search. We provide a number of different deployment options. We provide a managed service on top of the open source project that takes a lot of the undifferentiated heavy lifting of running OpenSearch and provides a service on top of it. You can also, of course, run it self-managed as an open source project. Additionally, we have a serverless offering that makes it easier to own and operate in the AWS cloud. Within OpenSearch, we have a plugin that provides a lot of the capabilities around vectors and semantic search. It's called our Neural plugin. It provides connectors to external model hosts. As you're running your data in, you can build pipelines that send out your documents to those embedding services, providing embeddings to come back in automatically. Additionally, at the search side, we provide a processing chain where you can run lexical, hybrid, or both of them, lexical, semantic, or hybrid, combining both of them to give you best of both worlds kind of matching. Supporting lexical, vector, and hybrid search. Additionally, we've done a lot of work and innovation on figuring out how to apply filtering for other metadata constructs as you're running your queries through semantic matching, again, to enable you to filter your data down, provide best matches within a filtered subset. If you're running on AWS, and as Easy and Anthony have pointed out, our EKS, Elastic Kubernetes Service, provides you a great way to run Kubernetes in the AWS cloud with its vanilla Kubernetes supporting the upstream version, 4 versions of Kubernetes supported, managed Kubernetes experience, and then administration operations support to make it easier to run Kubernetes. We also, of course, provide our OpenSearch service. So this is a managed version of the open source OpenSearch. It gives you easy configuration changes, 24/7 monitoring with self-healing and repair. Additionally, metrics to CloudWatch, audit to CloudTrail, integrated into the AWS environment. It is completely secure, providing encryption, TLS end-to-end, as well with audit and a number of different compliance, HIPAA, FedRAMP, et cetera. Provides number one, powerful search. So lexical search, semantic search, with a full search experience. It provides observability. So again, the distributed tracing, metrics, monitoring your applications, your hardware, your software. And finally, we provide a number of zero ETL integrations with other AWS services. So if you want to run your data in from Amazon DynamoDB, we provide an easy connector experience through our OpenSearch ingestion pipeline, where you can simply mirror your data from Dynamo to OpenSearch. Same thing for DocumentDB, and we are the default knowledge base for Bedrock. So OpenSearch is essentially in the databases family. The interaction model is going to be very familiar if you've ever used a database. You have your source data, could be logs, could be search data, could be vector data. You're going to format that and use, in Amazon OpenSearch service or for OpenSearch, you use a REST API to flow your data in. Within OpenSearch, all of your data is indexed. So in distinction to some of the other database technologies, OpenSearch provides indexing across all of the data that you send to it. On the query side, you simply send your queries via REST API. OpenSearch will search across the fields and indexes that you want to search and provide you with a ranked result. When you use OpenSearch, again, it's a REST API. You format your documents as JSON. This is an example document. It's a little bit small to read, but you can see we have a number of fields here. This is from the Amazon product question and answer data set. We have a number of fields, things like the question text, the category for the particular object, the question type, a number of answers. We can chunk it up. We have a brand name, item name, etc. So when you use OpenSearch, you format your data as JSON like this, use that REST API to send it in, and again, all of the fields are indexed and provide matching, fielded matching against that. When you run queries, there are a number of different ways to query, and in the semantic search world, the first of those is exact KNN. In this case, we use a filter on the price, and then we use a script score to say, okay, well, here's my vector, the query value, and I want to run a nearest neighbor search. This kind of query will do matching against every document in the index. Of course, we support approximate KNN as well, and you can see here we're searching with a KNN type query. We provide a vector embedding, a K for the number of results that we want to retrieve, and OpenSearch provides those results. Finally, OpenSearch supports a hybrid kind of query. Here we're supporting that through a search pipeline. So I'm using my REST API, I'm calling that search pipeline to engage with that query. It's a hybrid query, it has n clauses where n is up to 5. And I use each of those clauses is run concurrently. I provide in the search pipeline a weightage to say clause 1 should be 60%, clause 2 should be 40%, whatever, what have you, and a strategy for blending scores. So with OpenSearch Hybrid Search, you actually run multiple queries and are able to blend between them to get best results for both semantic, lexical, or multiple lexical, however you want to run it. All right, so we'll switch topics a little bit and talk about how OPEA is using OpenSearch. With OPEA, we have, again, our multiple microservices that are the OPEA microservices. AWS Professional Services has built out and contributed connectors to work with OpenSearch in the back end. We have our data prep and our retriever microservices. Those, again, just use OpenSearch at the moment as a sort of vanilla knowledge base. And looking toward the future, we'd like to engage with some of the additional kinds of query features that we covered in the first part of the talk. For the moment, it is using it as a vector store with nearest neighbor matching. So digging in a little bit to the data prep component. Data prep component uses OpenSearch to deploy 2 different indices. In OpenSearch, the index is the main container type. It's much like you have in a database table. The index collects all of the documents that you send to that index. The data prep creates 2 indices. One of them is a file index that creates an index across all of the files that have been put in it. It helps with the service to say, hey, you've already sent me this document, don't send it again. The vector store index is a vector store index. With the retriever component, it searches against the vector store. The chat application is going to call that microservice, going to search in the vector store. It is connected over the normal REST endpoints, and it uses LangChain to build the retrieval. So I mentioned a couple of different deployment options. You can self-manage, and both of these connectors will talk to your self-managed OpenSearch cluster. You can use OpenSearch Service. OpenSearch Service provides you, again, the managed cluster experience, and you can use OpenSearch Serverless, which is auto-scaled and hands-off. So all of the components that we built for OpenSearch are able to use any of the deployment options that we have for the service. I'm going to peel back the covers a tiny bit on OpenSearch and just talk a little bit about how the data is stored and how it's deployed. So OpenSearch is a clustered distributed database solution. It's deployed onto a number of different data nodes. So in this case, we have 2 data nodes, and within that, the data itself is deployed onto those nodes in shards. So when you create an index in OpenSearch, again, index the main container, you specify a partitioning, and data is equally distributed for that index across those partitions. OpenSearch itself then distributes those partitions to hardware, reactively to the hardware that's there. So in this case, we have a shard and its replica. Within a shard, then, we have a Lucene index that is the main lexical store that provides the ranked and relevant responses to lexical queries. We also have the vector native library index that stores the vectors and provides search on top of them. And in fact, on these data nodes, if you have multiple indices or multiple shards, the shards will get distributed across those data nodes. Each shard then representing a portion of the workload. So in this way, you can scale horizontally or vertically to provide more resources against the indices that you have, the data that you're putting into OpenSearch. OpenSearch scales quite large. We scale to billions of vectors, thousands of queries per second, because of the data distribution model. Of course, on top of this, we provide internally, OpenSearch provides caching that enables both for vector and for lexical faster performance for queries, where we have field caching, we have query caching, we have request caching, and vector caching. I wanted to say a tiny bit about capacity and how to scale for OpenSearch. The first element of capacity is storage. Obviously, if you're going to send 50 terabytes of data to OpenSearch, you need 50 terabytes at least of storage to hold that. If you add replicas, you need twice that much. So as you're thinking about capacity and how do I deploy OpenSearch, first thing to think about is storage. The second thing is compute. So your workload, as we saw, is distributed across a set of nodes, and each of those shards is a worker on those nodes. You want to put a number of CPUs in place proportional to how many shards you have. Because the shards are doing work, you need the CPU to run each of those shards. We recommend a shard to CPU ratio somewhere in the neighborhood of 1 to 1 or 1 to 1.5. Somewhere in that neighborhood, depends on the workload, a lot of different things. So with these two basic parameters, you can get a start at what's a good deployment for OpenSearch. Next thing is the instance type. You deploy instances then based on your storage and compute needs, and you deploy an instance count based, again, on your storage and compute needs. So this is how you scale and figure out how much hardware do I need to deploy. So I had a couple of examples. So we're looking at here, these are the different algorithms. We have HNSW, FACE, IVF, FACE, IVF with product quantization, and OpenSearch has a native quantization capability called byte quantization that reduces the number of bits used to store each floating point number, thus reducing the amount of RAM and storage needed for them. We look at 1 billion vectors with 384 dimensions. Depending on the algorithm, these are the parameters that go into either HNSW or IVF, and then code size is part of that too. How much metadata do you have? How much additional sort of structured information is stored with each object? And then this gives us a RAM need. OpenSearch, by default, will deploy all of the vectors into RAM. providing the fastest search. In our newest open source version, we support disk-based nearest neighbor search that pushes the full precision vectors to disk and then searches with reduced bit vectors. So this is the full RAM need and the total storage need. This gives us a sort of guide based on compute and storage and processor count and all of that I covered in the last slide. For 1 billion vectors at 384 dimensions for HNSW, you're looking at about 11 R7I larges, and across the board, 10 for IVF. If you apply product quantization, you can greatly reduce the amount of storage you need, the amount of vectors you need, greatly reducing the cost with the trade-off of accuracy. So that brings us down to 5. With our byte quantization, again, we get a nice reduction. These are 4x larges where the HNSWs are 8x larges. So this brings us down 50% or so in cost. We have now launched OPEA on the AWS marketplace. So if you want to grab OPEA and use it on AWS, you can get it in the marketplace as of now.
Amazing.
I'm going to hand it back to Easy.
All right, thank you, John. Great, thank you so much. All right, so we have some time, so we can show a demo, a really quick demo, just to highlight and to show you all the components. So, yeah, it says, just if I forget, I have the slide to remember. So that should be very easy to do. Here, okay, so nice. Nice, all right. So first of all, I would like to show you, if you go to the OPA site, if you go to the GitHub, you will see all the components and all the examples, mainly how the project is structured. When you go to the repo, you will see bunch of, some projects, right? But the most relevant are GenAI examples and GenAI comps. GenAI examples are these recipes, blueprints, or how you build the entire application, the end-to-end, using some components. And GenAI components are the components itself, right? So if you are a company or if you are a contributor that would like to say, hey, I don't like this, I would like to propose my own container, my own microservice, or I would like to add a functionality or something, you can go to GenAI comps and you can pick, for instance, if you go to the components, you will see all the components that are here. We talked about the retrievers, we talked about vector databases, we talked about the LLMs. Let's suppose we'd like to go to, I don't know, the retrievers, right? So, and these are all the retrievers that you have available to use in your configuration when you are building the end-to-end application. So Redis, Quadrant, you have all of them here, and you can do the same thing with data preparation, with the cores. So these are just the components. So this is the microservice. This is the recipe to build just a container, right? Just a microservice that is optimized for whatever that they are contributing. The GenAI example is actually the examples. These are the closest to the reality. These are what we mentioned at the beginning, like we don't just provide components, we provide real GenAI use cases. The chat Q&A is the example, like the RAG, the vanilla RAG, let's say. So if you would like to deploy, let's suppose a chat Q&A, you will go here and you have the options, right? So you have the Docker, you have the Docker compose file if you like to use on Docker, but you also will have the Helm charts on Kubernetes. So you go here, you download your Helm chart, and you can deploy it if you have the EKS actually deploy it. There is one step ahead of that, which is what OPA was working with AWS to have all these, some of those examples on the marketplace. So you just have to click to go to the marketplace, you find OPA, chat Q&A, and you can deploy it in your own cluster. So these are the examples, right? So, and something that I would like to mention is it's not just RAG, right? So if you have to work with agent, if you have to work with documentation, instructions, I don't know, search Q&A, visual Q&A, video Q&A, you have all these examples that are here, or recipes or blueprints to deploy in your environment. All of them with the Docker compose file and also with the Kubernetes version, so you can have the freedom to deploy to any environment you want. since it's an open source project, if you have a great idea and you would like to propose something, you can upstream, you can contribute your solution to here. So what I have here is I have already a cluster deployed with with the solution. I deploy the chat Q&A using Redis, and basically, I mean, I will not go in all the details just because of timing. But what I have here is a cluster, and it's exposed to a load balancer. And the end-to-end application will give you an UI, right? So you have an UI when you can interact. If you like to talk about, I don't know, what is OPA, we'll see that the model doesn't know, right, what is OPA, because it was trained, is using a model that was trained with information until 2021 or 2020, right? So we need to find a way to provide an external context, and the way to provide the external context, this example provides you two ways to do it. You can upload a PDF or a document, or you can create a link, or you can paste a link. In this case, I will go to the OPA documentation. There is an OPA docs page where you can investigate and you can see all the explanations, what are the microservices, what are the examples, how to deploy them, how to get started, and so on. But my question is, what is OPA, right? So I will go to the site which actually explains what is OPA, and I will copy this URL, and I will give to my RAG application that URL. You see that is what is happening underneath is, of course, the application is going to the site and is converting the text that you have in that site, is creating embeddings and is indexing that as a knowledge base. And it shows me here that it's already indexed. So now if I make a question, what is OPA? We have a question, we have the answer that we wanted to have, which is the context that we provide in the URL. This is a RAG. Most of you know what is RAG, of course, but the idea is to show that this is what you have when you deploy this blueprint. We can, if I have some more time, I can show you also the environment. I already did kube control, but these are the pods, right? This is the EKS deployment. So these are all the pods that were created, the TGI, the re-ranking. This is the Redis example because it's the common blueprint. This is using the UI and Nginx, so it's not just the components, it's adding some components, so you can, because it's end-to-end, right? So I have to have an UI, I have to add also an Nginx there. I already did kube control, so we can explore all of them, but actually what you will see when you explore it is you will see that each particular component is doing something. Right? If you like to do, if you like to know what the embeddings does, or the TEI, which is the microservice that is generating the embeddings, if you give a text, you will get the embeddings, right? So it's just like a simple, it's a microservices architecture, right? So it just works to do one particular function. And same for the TGI. The TGI is the LLM, so you can, if you curl it, or if you like to go very low level, you can curl it, and you can get like an LLM answer if you like to test that. This is why it provides the freedom. So all of those components, they are interchangeable. You can easily interchange it, but I have to build the entire example, right? So nice. So this is the demo. So I would like to show some more slides, and if we have more time, we will show it Q&A. Okay. That's not what you should see. Here. Yeah. Nice. Okay, so we have, this is something that we wanted to show you, that all the solutions that we work with partners, there's a program that works with partners and AWS. So all the solutions that you will see that are upstream or that are available on AWS, it's part of an accelerator program that interworks with partners, so they can also work with AWS. It's a pre-joint. And actually the idea is to enable the ecosystem and to propose solutions based on Intel hardware. I will ask my co-presenters to go on the stage. So if you want to scan, if you want to win something. All right, so no more scanning? Okay, nice. All right, that was the talk, so thank you so much. We will have 5 minutes for Q&A or questions if you may have. Thank you for your time, we really appreciate it, and we hope to see you tomorrow if you have some time. Thank you.
Thanks very much, folks.
Thank you.